So it says here that the angle theta is defined by the point -5, -3. So again, it's important to understand that the angle defines a position. So the coordinate defining the same position is just another way to define that same angle. So I'm going to draw that point in. So -5, -3. That's going to be in quadrant 3, and maybe it's going to be somewhere about here. Okay, so drawing that triangle in. So I have -5 here, -3. That using Pythagoras, I get square root 34 for that length. And again, the angle in standard position in this coordinate locates that same point. Okay, so there's theta. Okay, so that angle in standard position is drawn in there like that. And the primary trig ratios are sine theta, cos theta, and tan theta. And these ratios are to do with this horizontal and vertical positioning. Okay? And this sine, cos, and tan basically will translate angle positioning to x and y positioning. So our sine theta is going to be the opposite over hypotenuse, or more clearly, it's going to be y over the radius. Okay, this is how we're going to start defining it. It's going to be similar to opposite over hypotenuse, but we're going to say now the y position. So it's not 3, but -3, because we're now talking about y positioning, over square root 34. The cosine we're going to change from adjacent to hypotenuse to the x position. Okay, so again, the negative is important because we're now talking about positioning. The x position over the radius, so it's going to be -5 over square root 34. And tan is still going to be the slope, so in this case, it's sloping in this direction, so that's definitely a positive slope. So we're going to end up with -3 over -5, which works out to be +3 over 5. Okay, so that's our positioning, and we get our ratios from that triangle picture. And it's important to understand again that the positioning is defined as either an angle or a coordinate, and they both are locating the same thing. They're locating the position on the circle. Okay, so locating that point. Now the question does ask, what is the measure of that angle? We need to use the inverse for this. Okay, so I'm just going to use the inverse sine. Okay, so I'm going to use the inverse sine of -3 over root 34. Typing that into my calculator. I'm going to end up with, so inverse sine, that I get -30.96 degrees. Okay, so that's, my calculator is pretty smart. It knows standard position. However, if I look at that angle, I'm in the wrong spot, because that -30.96 is in quadrant 4, not quadrant 3. So if I were to draw that angle in, this angle here, okay, that angle is in the wrong spot. It looks more like here. And there's my -30.96 degrees. Now, it's actually in similar shape. In fact, it is the same shape as the triangle that I've drawn in quadrant 3. So if I want to actually get the right positioning, my arc sine doesn't always give me the right angle. It only gives me angles in a certain domain. So it only works, arc sine only gives me actually angles in quadrant 1 and quadrant 4. It never gives me angles over there. So I have to interpret this angle and work that angle out. So this is really going to be 180 degrees, and then I'm going to add the 30.96. In fact, I'm going to subtract the negative 30.96 degrees. And that's actually the proper way to do it. And the reason why we're subtracting is because from 180 degrees, I can subtract the same amount and I end up in the same y position, or I can add the same amount depending if I go backwards. If I go backwards, I'm actually subtracting a negative, which is positive. So I end up with 210.96 degrees. Okay, so we can get there any way you want. I'm actually using a formula for this, and you'll learn this formula later if you don't know it yet. But you could always just use symmetry, and that's because really that's where the real math lies. It lies in the symmetry, and the formula actually comes from the symmetry. So the angle that I wanted here, theta is equal to 210.96 degrees. And the thing to make note of is the arc sine, and maybe I will do this, just be a little bit more clear here. The arc sine, this arc sine always gives me angles in quadrants 1 or 4. Okay, it never gives me angles in quadrants 2 and 3. So if my real angle is in quadrant 2 and 3, I have to interpret the original angle, this is what we call theta 1, and interpret that angle and figure out where the symmetry is and figure out the angle on the other side of the circle. Okay, so this question here relates to exact values, because when we see 120 degrees, okay, that is a special angle. Okay, so 120 degrees lies right here in quadrant 2. And we make my reference triangle. This triangle is a special triangle. Okay, there's two of them. There's a 45 degree triangle. Okay, and then there's a 30-60 degree triangle, okay, which is half of an equilateral triangle. Okay, so this comes from, if I were to draw the other half of that, there's the other half of the equilateral triangle. And we should know these ratios because this is half the base. I'm going to say the base is 2. That makes the other side equal to 2. So this is 1. And using Pythagoras, I end up with square root 3 on that side. And so if I want to find the point on the circle of radius 2, it just works out that this radius and this hypotenuse work out exactly the same. So it's going to be 1 left, root 3 up. So I could do this. But again, I have to remember that I'm always interested in position. So this is not 1, it's negative 1 because I'm going 1 to the left. Okay, and this is positive root 3. Well, that's okay. That root 3, we have to make sure that we're in the right direction. So that's going to be negative 1, positive root 3's actual coordinates. So those negatives and positives start becoming important because we're talking about position in a circle. Where is it located? There's a big difference between right one and left one.